This airplane is undergoing a very unusual series of spin tests for a twin-engine general aviation airplane. Normally, spin maneuvers are strictly avoided in twin-engine airplanes and are prohibited as intentional spin maneuvers. These tests were performed by Beech Aircraft Corporation as part of its research efforts to develop new spin technology and apply it to general aviation aircraft. This spin research program has proceeded with active cooperation from the National Aeronautics and Space Administration, which is active in a broad basic research program to develop the technology required to improve the stalling and spinning characteristics of light general aviation airplanes. Beech Aircraft Corporation has actively supported this NASA research program and concurrently has been developing the technology to apply NASA research to production aircraft. Beech's first major opportunity came in 1974. Beech was awarded a Navy contract to design and produce the Model T-34C turboprop-powered basic training aircraft for the Navy. Because this aircraft was designed for a fully acrobatic mission, including spins, the Navy sponsored access to the NASA Langley Spin Tunnel. Beech engineers worked side by side with NASA in a program to attain the fully developed spin characteristics required for the Navy training mission. Paralleling the NASA spin tunnel testing was a Beech program of full-scale development flight tests which included over 1,200 spins. This combination of spin research techniques ultimately resulted in achieving the characteristics desired by the Navy. This program also provided the impetus for Beech Aircraft's development of radio-controlled scale model techniques to study spin characteristics. This was done by spin testing a T-34C radio-controlled scale model and comparing the results to the flight test and spin tunnel database already in hand. Following the T-34C, Beech was allowed to purchase time in the Langley Spin Tunnel to conduct tests on a civilian Model 77 Skipper aircraft. The first time the Langley facility had been made available to a general aviation manufacturer for a civilian project. Later, Beech was allowed to purchase spin tunnel time for the Model F-33C acrobatic bonanza tests. All of these aircraft are single-engine aircraft. Although the NASA General Aviation Spin Research Program had been limited to single-engine aircraft, Beech Aircraft Corporation, building on its experience, was ready to extend its own research program to a light twin-engine aircraft. If successful, this would represent a major advance in the state-of-the-art of spin research. The logical candidate was the Beechcraft Model 76 Duchess, an airplane Beech had under preliminary design consideration in 1975. The Duchess was envisioned as an aircraft to fulfill roles of utility flying, charter flying, and multi-engine training for Beech operators. Since it was a new design, it offered the opportunity to incorporate state-of-the-art concepts. Also, it was lighter in weight and had a relatively unsophisticated wing design compared to most general aviation twins. Exploring the spin regime in a twin required Beech aircraft to develop and apply new technology and to test well beyond the FAR requirements for this class of aircraft. A combination of newly developed testing techniques were implemented in the course of the Model 76 Spin Research Program. Early in the Model 76 development program, it was decided to construct and flight test a radio-controlled scale model of the Duchess to give foresight into the stall spin area, using the experience gained from the T-34C radio-controlled model tests. A 7-foot wingspan model was constructed using standard model aircraft techniques. It was loaded with weights to simulate the full-scale weight, CG, and inertia yawing moment parameter. Included in the model was a telemetry system which sent aerodynamic data to a ground station. When the pilot flew the model into a spin, angles of attack and side slip, as well as rudder, elevator, aileron, and throttle commands were recorded for immediate use by the test engineer. This information, coupled with movies, enabled a detailed analysis of the spin to be done. A total of 68 spins were performed, and they showed acceptable spin and spin recovery characteristics. Because of the basic aerodynamic principles involved, every twin-engine aircraft has a tendency to spin when stalled with one engine inoperative. While spin testing is not required by the FAA for twin-engine aircraft, the FAA does require a demonstration showing that the aircraft displays no undue spinning tendency. Since the Model 76 was to be used in multi-engine training and transition, the FAA requested that Beech take an unusually comprehensive look for any undue spinning tendency as a part of the FAA certification process. Beech and the FAA agreed on a test program to accomplish this check. As a part of this program, stall recoveries were delayed up to and including 1 turn into the incipient spin. These were demonstrated with power off both engines and, as in this case, power on one engine only. The spins with both engines at idle were entered using standard FAA procedures with slow deceleration to near stall. Full rudder was then applied in the direction of the spin desired, followed by full up elevator. Full rudder, full up elevator, and neutral ailerons were held until recovery was desired. Recoveries were made using full opposite rudder and nose down elevator. Recoveries took 1/4 turn or less. Single engine spin susceptibility tests were conducted with one engine at idle power and the other at maximum continuous power. In this case, the stall was entered by slowly decelerating with one engine at idle, and in other cases the engine power was abruptly reduced to idle at the stall. The test results showed that the Duchess will pitch and yaw in the stall, but not necessarily enter a spin. If 5 to 10 degrees of bank can be maintained, the aircraft can be controlled indefinitely. If the angle of bank is allowed to decrease to near level, the aircraft will slowly roll and yaw into the idling engine. Continued use of full up elevator and single engine power at this time will lead to a spin entry. Recoveries were made in the standard manner. As a part of the testing program, many of the recoveries were made without reducing power on the good engine. All recoveries were 1/8 turn or less. Once the FAA certification program was completed, Beech continued its spin research program by exploring the spin characteristics of the Model 76 beyond the 1-turn point. In order to gain additional background knowledge before embarking on further exploratory manned airplane flight tests, a broader model testing program was undertaken. A rotary balance wind tunnel test was run at the NASA Langley Research Center, utilizing the same 7-foot wingspan model previously used as a radio control model. Rotary balance testing is a new state-of-the-art technique used to measure the forces and moments on a model subjected to the rotary airflow existing during a spin. The Beech Model 76 spin program was the first industry use of the Langley rotary balance system. The model was equipped with a 6-component balance which transmitted force and moment information directly to a mini-computer where aerodynamic coefficients were calculated and displayed. Information was gathered at different spin rates and angles of attack so that the whole envelope of the steady-state spin could be analyzed. This was followed by testing a model in the NASA Langley Spin Tunnel to study developed spin and recovery characteristics in free flight. Like the rotary balance test, spin tunnel tests were on a fee-paying basis. In this case, the model was made primarily out of balsa wood and had a 32.5-inch wingspan. It was loaded to simulate the full-scale aircraft's weight, CG, and inertia, and contained a one-shot trip device to activate the control surfaces for recovery. The results indicated satisfactory characteristics, both in a steady-state spin and recovery. The spin tunnel was also used to size an emergency spin recovery parachute for the test airplane. A number of parachute diameters and canopy lengths were tested to build a matrix of data. Information was also obtained on pilot escape procedures using a simulated pilot released in the developed spin. Over 170 different test conditions were examined for a total of about 500 spins. Spin testing is one of the high-risk areas of flight testing. Only with careful planning and preparation can it be conducted safely. It begins with a test pilot being checked out in an aircraft of proven spin capability. Spins can be highly disorienting maneuvers and require that the test pilot be both proficient and current in spins in order to perform these maneuvers safely. An emergency spin recovery parachute is fitted to the test aircraft. This ensures maximum survivability for the test pilot and the test aircraft in case the flight controls are found not adequate to recover the aircraft. Reliable working of the spin chute system is essential, and it was subjected to much proof testing, both on the ground and in the air. Fortunately, the Model 76 was found to have excellent recovery characteristics, so the parachute was never used in an actual emergency recovery. The flight test airplane is fully instrumented to measure the pertinent aerodynamic parameters. Test information is telemetered to a ground receiving station where engineers monitor the data as it happens and where it is recorded on computer tape for later, more detailed analysis. Only after all background checks are completed and systems working is flight testing initiated. The flight testing was performed using a team concept consisting of test pilot and test aircraft with instrumentation, chase aircraft with a test observer and cameraman, ground telemetry station with real-time plotting of key parameters such as angles of attack and side slip, airspeed, control positions, and angular rates. 3 basic types of spins were looked at: both engines at idle power, both engines at full throttle for the first turn then brought back to idle, one engine at full throttle and the other at idle for the first turn, then both at idle. A wide range of loadings from mid to aft CG and with both full and minimum fuel. Pro spin controls were held for as many as 6 turns. The resulting spins demonstrated acceptable spin characteristics. The aircraft was readily recoverable with conventional recovery controls. The effect of asymmetric power on the spin was surprisingly found to be relatively unimportant to the developed spin characteristics or to the recovery characteristics. Several spins were made without the spin chute installation to ensure that it had not affected the spin or recovery characteristics. The total flight test program involved nearly 150 spins, with the data reduced to a time history format for detailed analysis. The Beech Model 76 spin research program had been a step forward in the state-of-the-art of spin technology. In the course of its research, Beech developed and used new technical tools and techniques. Testing of radio control models, spin tunnel models, and rotary balance models provided early visibility into the spin and spin recovery characteristics. The flight testing program proceeded safely and with a high degree of confidence. The spin characteristics of the Model 76 were found to be acceptable and the aircraft readily recoverable. The Model 76 Duchess Spin Research Program was performed with a spin-experienced engineering test pilot and was successful. The success of this program does not change the operation or certification of the Duchess. As with all light twin-engine aircraft flying today, the Model 76 Duchess is placarded, normal category aircraft, no acrobatic maneuvers, including spins, approved. Safe flying, as always, depends on observing prescribed aircraft operating limitations. The Model 76 Duchess Spin Program is an important milestone of Beech Aircraft's continuing research program to improve aircraft safety. This has been a presentation of the Beech Aircraft Corporation.